And again, hello everybody, and welcome back. I'm glad you're here, and I again invite you to subscribe to the YouTube channel, my YouTube channel. The name of the channel is Patrick Gray, and I would be happy for you to be there. This is a series of discussions about a heavy lift drone, big enough and heavy enough to carry people for a military use. I am exploring exactly how this could be put together and what would be involved. We're up to part 6. I thought, and we do have the story of our military service person who has been chosen to run this program and fly the heavy lift drone, and I thought we were going to have him flying. But I realized in my discussion of one of the parts that I don't know that I did a completely most clear explanation of it, so I'm going to go over a little bit of that first. And we are looking today at Field of Lavender in Somerset, England. And again, we always try to start out by telling you any physically real item could hurt people or damage something if it's not properly used or operated. And we advise do not make any physically real item unless you can manage it in a way that is legally allowed and reasonable and safe. And if you can't do that, then we suggest, or I suggest, don't create a physically real item. And we again want to remind you that we have these drones. Here is a forward operating base next to a river. This is 50 meters right there. Here is the facility. It has a protected roof, and we keep the drones inside this facility, and we bring the drones out to fly them as needed, depending upon whether there's something going on somewhere where the drones are needed, and they're brought out from their protection, and they generate a sufficient lift to take off in a VTOL manner. And we are discussing that there are a number of drones that are available. One drone that we think the base is going to keep wanting to have is the big one. That's this one, 47-foot wingspan. It has 6 propellers that can go and generate vertical thrust to make it go straight up in the air. So it takes off going straight up. And then these propellers can have a tilt rotor function and can be tilted down to generate horizontal thrust. And this plane starts flying based on horizontal thrust. It generates enough airspeed that the lift from this wing is enough to hold up the plane. And it's big enough to put 2 or 3 people in it, and about 2,000 pounds of payload, maybe 14 or 1,500. It's not quite clear. And it runs on 2 of the Rolls-Royce Allison 250-C47 or C30 turboshaft jet engines that are running hydraulic pumps, and the hydraulic pump flow goes through a control manifold and sends it out to these propellers. And the issue that we're discussing is that it takes whatever amount of power it takes to get your drone to go straight up, based on what I call drone flying. Drone flying is where the lift to keep the drone up in the air comes from the propellers. So that is drone flying. And the amount of power required for stable hover with drone flying, to get the same amount of lift from a fixed wing flying with the plane flying through the air, the amount of power required to keep the plane flying through the air is about 1/10 of the amount of power required to get the plane to go up in the air with the propellers lifting the plane and keeping it up in the air. And the issue that comes up is you have to have about 800 horsepower to get this plane, when it weighs 5,100 pounds, to go straight up in the air. But you only need about 90 to 100 horsepower to make it fly along. So you need a lot less horsepower. And we are suggesting to fly it along at a lower speed, like 70 to 90 miles an hour. I know that there would be the thinking process that this constitutes a very easy target to shoot down at that speed, but I would want to propose for it to fly at 9,000 feet altitude, which puts it above a lot of normal munitions that just regular units would be carrying. And I also am wondering, maybe on this drone itself, but perhaps a second drone that would take off a little drone and fly with it. The littler drone would run off of one of these engines. That littler drone, again, would use a lot of its engine power to get up in the air with VTOL, but once it's up in the air, it only needs 40 to 50 horsepower to fly along. So this little drone can fly for 7 or 8 hours along with this, and the little drone uses its excess or some of its power to generate an electronic countermeasure. So that allows this to fly along at 70 or 80 miles per hour, and it won't be hit by missiles. It may not even be detected. And this allows us to address the issue of what can we do about having 800 horsepower worth of power capability, but we don't want to spend the fuel to keep an 800 horsepower system running if the drone doesn't need 800 horsepower to just fly along. We had mentioned the hypothesis that this drone system, particularly this large drone that can carry supplies and equipment and ammunition and wounded people and might be able to have a weapon system in it, that flies along with it the little drone that provides electronic countermeasures, this may become effective enough that enemy forces begin to lose their interest in the battle, and there's less combat activity that occurs, enough that perhaps this drone might not get enough use where you're happy that it is properly certified and properly evaluated and ready to be used, because it just isn't used that often. And we proposed a separate system that would allow us to test and certify and calibrate the jet engine of this drone, even in the situation where the drone is not really flying that much. And we made the proposal of consideration to have a Parker Hannifin F11-5 small hydraulic motor attached to the starter motor of the jet engine, so that the jet engine could be spun up to speed even though no fuel was flowing and there was no heat or pressure in the combustion chamber, but you still could spin up the N1 turbine of the jet, and there might be enough airflow to get some spinning of the N2 turbine, but you'd be able to spin up the jet engine for the purpose of testing it using this system, which we talked about. And I'm a little nervous that when I was talking about this, I may not have completely described it, so I wanted to talk about it just a little bit more. Okay, and as I was talking about it, I had mentioned that this disc, this is a clutch. This is a one disc clutch. The blue is part of the clutch and the purple is part of the clutch. And we can All right, this part of the clutch is one, and I've altered the opacity of this material so you can see through it. This just helps to understand how it works. The real material, and they're different colors, but the real material, you would not be seeing through it. And this yellow material is a cap that sits on top of the starter motor, and the shaft of the starter motor is brought up to this shaft here. And this shaft has this appearance, and this curved section of this shaft is touching this ball bearing system, and the curved portion of this shaft goes all the way up and is anchored by this bolt to the upper portion of this spindle. And this spindle, as you can see, has a rounded surface as part of the spindle. And so when you look at this in cross section, what is happening is the lower portion of this shaft is got a circular structure that pushes on these ball bearings, and the upper portion of this spindle has a circular portion that's pushing on these ball bearings, and these ball bearings spin around in the raceway of that piece of the structure that I just made invisible, which is this structure. And to summarize, this spinning portion of the clutch is sitting as a spindle in a axial radial stabilized thrust bearing, so that when you push down on this pushes down on these ball bearings, which pushes down on this, which pushes down on the casing of the starter motor. And so any amount of axial force that you put onto this disc, that axial force is not translated or placed onto the shaft of the starter motor. So you're not pushing down on the shaft of the starter motor. You're pushing down on this radial axial stabilized thrust bearing. And if you look at this Parker-Hannifin F11-5 motor, if you go to the Parker-Hannifin site and look at this motor, inside this motor, the shaft of this motor is also connected to an axial radial stabilized roller bearing thrust bearing. And the effect of all of this means that you can take this motor, so if you take hydraulic fluid and put it, not here, but put it here, then this is fixed. And so this piston will go up that way, but since this is fixed, what happens when this piston goes up that way, that's not really what happens. What happens is this motor goes down this way. And when this motor goes down this way, it takes this plate of the clutch and pushes it against this plate. And if you look at clutches, there are several issues associated with clutches, including the use of clutches where the item is turning and creating a torque, and you have to engage and disengage the clutch where it's carrying a torque, which we're not doing. So the only times that this is going to be engaged and disengaged is when both shafts are not turning, and we push it together and then we start it turning. And another issue with clutches is to have enough clutch friction that you don't have slipping of the clutch disc. And one way to change that is to add discs where you have 2 or 3 or 4 discs in a stack with a spring arrangement. Another way is to increase the diameter of the disc. But there's a third way, which is to increase the pressure, the force of the compression pressure between this disc and that disc. And this system is constructed and structured, since this is a radial axial thrust bearing on this disc, and we also have a radial axial roller bearing on this disc, and we have a hydraulic force system. We can get significant downward force from this motor onto this disc, and this disc is pushing down onto that disc, and these two discs are pushing fairly tightly against each other so that the clutch will not slip, and we're not putting any of this radial axial force onto the starter motor. And I did not really explain that, I think, very clearly, so I wanted to explain it. And it may be, again, since this is a radial axial stabilized thrust bearing, it may need to have, it will need to have oil, so you're going to have to bring oil up to it and oil back away from it. But the turboshaft jet engine has a pressurized oil system. And over here on this, again, I thought maybe this might be too long, so I folded it over. So this is long but thin. This is short but fat. So would be up to the jet engine people which one they wanted. But again, this the shaft of these gears is attached to this same radial axial stabilized thrust bearing, so that as this motor is pushed up and this disc is pushed against that disc, we're not generating any net upward pressure on this gear system. And so this gear system has no axial pressure that it's putting on this. This gear is connected to the shaft of the starter motor. But again, there's a radial axial stabilized roller bearing in the motor, and there's this radial axial stabilized ball bearing for this spindle, so that as we again use hydraulic force to push up on this, we're not putting axial forces on this gear, and we're not putting axial forces on this gear. These gears are connected to the starter motor, but there's no real significant axial radial strain on the shaft of the starter motor. And the purpose of this at this point in this discussion was to make the discussion point of spinning up the jet engine for the purpose of certifying it and testing it. But another completely separate issue is the question of, you need a lot of power to get VTOL, vertical lift and vertical landing, or vertical lift for the purpose of takeoff and the purpose of landing for this drone. But once it's up in the air and flying and has enough airspeed to generate lift from its fixed wings, it doesn't need anything like 800 horsepower. And it is wasteful to be running 800 horsepower worth of jet engine when you're only asking to have 90 horsepower from it. So that is another way that this clutch system can be used for a purpose that is different from simply just testing the drone. And so we were working on a completely separate problem, which is, first of all, there's a fuel efficiency issue of running 800 horsepower worth of jet with an engine that is on, even on idle setting, when you don't need it. That uses up fuel. But there's a separate issue of taking an 800 horsepower engine system and trying to extract only 90 horsepower from it and not the other 710 horsepower, because the jet engines are typically constructed to be optimized for certain power outputs. And a question becomes, it may be with this drone, there's room in the DHC-2 de Havilland model to put, Rolls-Royce has a 300 version of their Allison 250. It's their most modern version. It's 220, 230 horsepower. It could be that the Allison 250 or the Allison 300 should be in the drone to be the engine that powers fixed wing cruising flying. And then there's another jet engine made by Pratt & Whitney. This other engine, and this engine had been used in the de Havilland, the Pratt & Whitney PT6B-37A. This has 900 horsepower. It doesn't have quite enough torque specifications to get the DHC-2 off the ground by itself. But, and here what I did is, here's what that engine looks like. It's not exactly the same configuration as the Rolls-Royce Allison 250. So I took my Rolls-Royce Allison 250 model and kind of just changed it around so that it looks like the Pratt & Whitney. But what can be done is to take the de Havilland and put this Pratt & Whitney PT637A turboshaft jet engine in it, and also put the Rolls-Royce 300 engine in there. And the Rolls-Royce 300 engine becomes the engine that runs it for cruising, and the Pratt & Whitney PT6B-37A becomes the engine that is used to get it to add enough power to bring it up into the air. So basically you run both engines to get it up into the air, or just one engine, the little Rolls-Royce engine, for cruising. And this Pratt & Whitney also has an electric start and a starter motor, and can have added, I think right here is the power takeoff, but somewhere on this engine is an electric motor for starting it. But if we go back to this design, which is the Rolls-Royce Allison 250 engine, you need two of them to get it to go up in the air, but you only need one of them to do cruising or fixed wing cruising flying. And we did modify the air intake to address the issue of how to run this engine efficiently at 90 horsepower. But the final point that I wanted to make on this clutch system was, this clutch system could be a way in which one of the engines could be not exactly turned off, but cycled down to a very low power condition that would allow the cruising of the plane to be occurring with only one engine running at 90 horsepower and the other engine running at 10 or 12 horsepower, just enough horsepower for it to have a high probability that if it was needed to be started, it could be started. And the flying issue that we're discussing here is, you run both engines, you extract your 800 to 900 horsepower and go straight up in the air, and then you start it doing fixed wing flying, and you say, all right, well, we'll just turn this engine off. And you now are in a situation where you can't land. You actually can land. You can land on a runway, or you can land on the ground doing just regular flying. But we don't want to do that, because there's tremendous advantages in not having to land on a runway, including you don't need a runway. In addition to that, pilots who are flying the plane, it's one thing to have the central processing unit bring it to a stable hover and just go straight down and land. That's totally different from flying down into an airfield and landing on it at 90 to 100 miles an hour. So we don't want the plane. We want it to be, if you turn your engine off, that needs to be a serious consideration where we want to turn this engine off where we're really happy that we have the belief we're only turning it down. If we want to get it going again, that's not going to be a problem. And we went out on the internet and just looked for some information. This is helicopters, but this is the engine that is running. Let me rephrase that. Many helicopters use the Allison 250 engine as their engine, and that's what this is discussing. The 250-C20/20B. And what we're looking at is if you put it on idle, normal idle speed, just put the engine on idle. So you're flying along, you turn one engine to give power for flying, fixed wing flying, and we got it into a stable condition at 90 horsepower with the forced air intake that we were talking about, and the other engine we just turned to idle. And it looks like they're saying that idle is 47% of N1. So the way these engines work, the thermodynamic principle that requires enough heat in the combustion chamber to generate enough pressure in the air to spin up the N1 turbine to give it enough spin for it to be a stable running condition, winds up being at 47% of N1, which is N1 is the combustion compressor turbine. And we found this paper. This paper is from, looks like 2012, looks like Germany. They were working on the issue of, they have helicopters with two engines because they need them for certain activities. But a lot of the time when they're flying, they don't need both engines. And if they run one engine on idle and just use the other one, they are using up a lot of fuel, and they are running engine hours on the engine that they're not using for any power. And they were addressing the issue of, well, what can we do to bring an engine to a condition that's using a lot less fuel? But they had the nervousness of, if you take an engine to a condition where it's using a lot less fuel, like for instance, turn it off, if the other engine that you're using fails, you become a helicopter with no power. And a helicopter with no power is a serious problem. Whereas on the de Havilland DHC-2, it's a fixed wing flying plane. So anytime you have no power, it's a serious problem. But it can just start gliding, and it's a lot more stable, and you have more time to figure out what you're going to do, both to decide how to land if you have to, but also to go through procedures to get your power back, than you do with a helicopter that now has both engines not working. So they are talking about the issues and concepts related to powering down an engine, but they want it to be powered down where they can get it back in 8 or 9 seconds. And so that's what they're really discussing. But they are discussing the issues associated with running a helicopter engine on idle and chewing up fuel. And so we'll go over a couple of issues. Like, for example, I think it was 47% of N1, but even down in the 35% range to 47%, you're at looks like 0.007 or maybe 0.008 kilograms of fuel per second. And so let's pick 0.008. So 0.008 kilograms per second times 60 seconds is that many kilograms. That's 1 minute times 60 minutes is 1 hour. And if this is going to fly for, say, 4 or 5 hours, it's 144 kilograms of fuel, which is 316 pounds of fuel to run that engine on idle. That's a lot of fuel just to have an engine that's running that isn't doing anything. And they went through some scenarios where you turn the engine off, you turn it off, but you spin up its gas generator turbine, the N1 turbine, and you spin it up by connecting it to the power turbine of the engine that's running, and you run one at ground idle, and then you try running the engine at a sub-idle condition. And you can see as we slow the engine down to idling, particularly if we start giving it power from the other running engine, the amount of fuel that it requires is much less. And one of the things they mentioned was, if you really bring the N1 turbine of the non-powering engine down to what they consider about the lowest safe level you can get at, 35% of N1, it only requires 11 kilowatts of power. So if we need 11 kilowatts just to spin up the non-powered turbine at 35% of N1, and let's see, that's going to be it. The N1 turbine is 55,000 RPM. So that would be spinning that turbine at 19,000 RPM. We can pull up our power conversion program, power, kilowatts to horsepower. So 11 kilowatts is 14 horsepower. And we happen to remember that the engine, the Allison engine, runs at 0.6 pounds per fuel per hour per horsepower. So 0.6 pounds of fuel per hour per horsepower times 14 horsepower is 8.4 pounds of fuel per hour just to spin up that non-functioning engine, times 5 hours is 40 pounds. So it would require 40 pounds of fuel to keep that engine spinning instead of 300. And that's with it spinning at a very, very low rate, not really at a successful heat-based thermodynamic turbine heat cycle, but just spinning it along at 19,000 RPM. 42 pounds of fuel is a lot less than 314 pounds of fuel. And they go on to show some discussion about trying to get this helicopter lowering emissions because they're not using it, and trying to get the helicopter going in a quick amount of time. And they have an air pressure system to spin up the compressor. But all of this is related to them trying to get that engine going in a hurry, which is not an issue for us. And we'll go back over here to this clutch plate, single disc clutch system to spin up the starter motor. And by spinning up the starter motor, it allows the starter motor to act as a generator. So you have the electrical output, and you also have the N1 turbine spinning. And the question is, can we spin it maybe not even at 19,000 RPM, but maybe spin it at 6,000 RPM? Just enough spinning of the N1 combustion turbine so that the sensor system of the jet engine is working and we can make sure it's okay. And we have a little bit of some spinning of the power output turbine so that we can run our engine sensors for that side of the engine also, and we can also check for oil pressure and electrical and everything about the engine to reassure ourselves that probably this engine is okay. And now we're using this to spin up the engine when you're flying so that one engine can be used to supply 90 horsepower for fixed wing flying, and the other engine, it is in a multiply lowered action state where it's just available, but it's not using up all that fuel because you don't need it. And the final thing I wanted to mention was I called this a combustion cap, and here's 4 of them. And here's my way of trying to draw flame. You know, here's no fuel coming out. Here's a little more fuel coming out. Here's more fuel coming out, and it heats up and makes these flames. And here is what this looks like. And the purpose of this structure is it has a hole in it that you can see through here. There's the hole that goes through it. And inside of it, if you look inside of this device, is a metal band. And this device is a ceramic material that can withstand high pressure and high temperature. And what you do is you put electrical power on this metal band and you heat this thing up so that it is significantly in excess of the combustion temperature of the fuel. And remember, if this is connected to a pressure system and fuel, there's a fuel line here that's bringing fuel into this, that fuel line doesn't have any oxygen in it. It just has fuel. That's how fuel lines work. So even if this is warm, as this fuel comes up through here and begins to flow through this channel, this fuel is not going to combust because there's no oxygen. And what it's going to do as it flows across this ceramic insert is going to heat this fuel up in excess of its combustion temperature. And so when the fuel comes out into the combustion area and contacts oxygen, it's going to light itself on fire and start burning. And if you want more flame, you add more fuel flow. And if you want less flame, you add less fuel flow. But you never have to worry that the flame will go out, because it almost can't go out because the fuel is at a temperature in excess of its ignition temperature. So the advantage of this is you can have a very low level combustion going on where there's almost no way that the combustion can be turned off. And you might put this in that jet engine combustion chamber where the main fuel input cap injector is right here. And so instead of injecting enough fuel through the engine to light up the combustion chamber and bring it up to 1200 degrees, or full power is 12 to 1300 degrees, idle power is probably 900 degrees. You're not bringing it up to that temperature. You're just pushing some fuel through here to have a flame on the inside of the combustion chamber and maybe bring it up to, well, it's going to be at 200 degrees because the air was compressed. But again, you're not spinning it that fast. So my guess would be you would have a combustion chamber that was at maybe 200 degrees, and you'd just be putting some fuel in here that's on fire, and the entire jet engine would be running in a very low state of activity. It would be running perhaps at an N1 of 5,000 RPM and a combustion chamber temperature of 300 degrees and a combustion chamber pressure of maybe 1.2 atmospheres or maybe 2 atmospheres, 28 pounds per square inch. And what happens when you do that is you've got that engine as close to working as you can get it without it working. And it doesn't require its compressor to be efficient or functioning well. It doesn't require its N1 turbine to extract power from the combustion gases, and it doesn't require its N2 turbine to supply any power to the pumps, because we're not asking it to do any of that. And the reason why this jet engine is spinning is because we spun it from that hydraulic motor. And so nothing about the heat cycle of this engine is required to be functioning. And the other advantage of this is when it became time to ask for this engine to work, you just start spinning it faster and faster with that hydraulic motor and bring it up to an N1 in the zone that they think might allow the jet to work, like 15% of the normal N1 or more. And you gently bring it up to speed and you begin to increase the fuel flow rate to a fuel flow rate where there's enough combustion of fuel to pressurize the combustion chamber and to bring the entire jet engine up to putting out power. And what would happen is you would cruise along in fixed wing flying using one jet with that air intake propeller that I discussed, so it's stable at 90 horsepower. And when you are within 10 to 12 to 14 minutes predicted of beginning to switch to VTOL, you would take this second jet engine that you had been running at a very, very low heat is present, combustion is occurring, but it's all very low power, and you would start spinning it up slowly but surely in a careful and measured way to bring it into a condition where you can get it started and capable of putting out power. And you would instead of starting it over a period of 1 minute, you might start it over a period of 7 or 8 minutes. You don't care, because your control of how it spins is from that hydraulic motor, not from putting electrical power into the starter motor. And you are not requiring it to have its compressor working or generating heated gases to spin up the N1 turbine until you're ready to do it. So you spin it back up, and then you start adding more fuel, and you monitor your parameters. And when it's at a zone where you like what's going on, then you can really start putting the fuel into it, turn off that hydraulic motor, disconnect that clutch, and it becomes a running second jet engine. And I just think that I didn't explain all that clearly or in enough detail. So we've got Charlie basically in suspended animation, just standing there looking at that phone, dreaming about his cheeseburger. He's very close to getting ready to have a lot more of a flying adventure than he thought he was going to have. But I put him in suspended animation for a few moments to make a more detailed discussion of this clutch hydraulic motor power system that I wanted to discuss more carefully.